Heyo, I'm Andre, also known as AP-AAiS. I'm still the owner of this channel, and I'd like to welcome you to this third and final installation of the German Kid Does Something having to do with Game Boy, the Raspberry Pi Pico, and MIDI series, where we now explore different approaches of achieving 16-channel MIDI playback on the Nintendo Game Boy. Now, across the last two videos, we've explored, designed, and built two different systems that can connect up to 4 Game Boys to a classical MIDI interface such as the Arduino-BOI or my own MIDI-BOI. Both of these interfaces use the power of a microcontroller to translate UART formatted MIDI messages into the clock and serial signals of the GameLink protocol. Thanks to both of these previous approaches, we've essentially already been given all the tools that are needed to achieve the playback of all 16 MIDI channels across 4 interconnected Game Boy devices. Accordingly, the overarching goal of my master's degree, aka the conceptualization of an easy-to-use system that can facilitate the playback of all contents within a MIDI file, has also been achieved, meaning that I could, realistically, have just left things off here. However, despite the single interface link system in particular being both easy to set up and subsequently use, there remains one big problem which has continued to loiter in the background of all my prior work on these 16-channel Game Boy MIDI systems. Pricing. More specifically, I'm talking about the price of the previous multi-interface link and single interface link system hardware. Since each Game Boy audio processing unit only provides us with 4 sound generators, we will inevitably need at least 4 different Game Boys to play back all 16 channels of the full MIDI standard. To run a version of the Game Boy software MGB, which is needed to translate the MIDI signals that our MIDI interface sends out into actual sounds and instructions on the side of each handheld, we will also need to buy at least 4 Game Boy/Game Boy Color Flash cartridges, as well as 4 SD cards on which to store the MGB ROMs. Finally, both of the previous setups required us to also purchase either a MIDI-BOI or Arduino-BOI MIDI interface to take care of the signal translation work, as well as several GameLink cables to connect our Game Boy with the microcontroller of the interface. In total, these costs obviously add up immensely, which isn't great. If you're just a simple composer or chip music fan that would like to work with these expanded capabilities of the Game Boy at the lowest price possible, paying several $100 to build your own multi-interface or single interface link system is obviously a hard sell. As someone who did end up paying the many upcharges throughout the creation of both of these interfacing methods, I understand this problem decently well myself. Really, without any steady income in my university years, I had more than enough cause to start thinking about different potential cost-cutting measures. And even before the start of my master's degree, I found myself asking one simple question. Since I am forced to pay for at least 4 different Game Boys to conceptualize and realize my methodologies for an all-channel MIDI playback, couldn't I use one of the handhelds of the system to parse a MIDI file directly? After all, the only purpose the MIDI interfaces of our multi-interface link and single interface link networks served was to translate the signals of a MIDI source into the GameLink protocol, which the Game Boy obviously speaks natively. The sequence of events that this initial thought set in motion, over the course of many sleepless nights, ended up in the creation of 2 different software suites, called MIDI-Dumper-GB and MIDI-BOI, which, for the first time ever, now actually do allow you to play back MIDI files on the hardware of your own Game Boy. To understand how these components work and how you can use them for yourself, I'd like to tell you a short story for the course of this video. A story about adversity, of desperation, and of making something work that realistically shouldn't work in the slightest, yet runs with the precision of an Italian train. This video will detail the history of how I got the Game Boy to play back MIDI files. Barely. Welcome. Welcome to the story of MIDI-BOI. To start off the section, you might be asking yourself the simple but rather poignant question of, wait, can the Game Boy even parse MIDI on its own? After all, MIDI files can reach several megabytes in size, and the signal information they encode needs to be rather complex for a song to attain its needed timing accuracy. Well, I think that's a great question to begin my retelling of MIDI-BOI's history, and to give you the short answer right away, no. The Game Boy is not actually powerful enough to be compatible with the MIDI standard, not even in the slightest. However, just because something is fundamentally incapable of serving a standard, doesn't mean that we can't still just brute force our way into getting things to work, reality be damned. Just like those Penske drivers at the 12'4", formerly 11'8" bridge in Durham, North Carolina, we can make use of the age-old philosophical concepts of violence and sheer mindless determination to push our semi-truck, or in this case Game Boy, into places that our insurance certainly won't ever cover. Before we get to that point though, it'd be prudent for us to first figure out the limits of the hardware that we'll be working with from here on out. Once we know what factors nominally all want to prevent us from playing MIDI files on a Nintendo Game Boy, then we can begin to work our way around all the many hurdles a late 80s handheld platform puts into our way. So, for this first section of the MIDI-BOI story, let's get ourselves familiar with the Game Boy hardware. For reasons that should become obvious rather soon, we'll actually discuss both the hardware of the original Game Boy as well as the hardware of its successor, the Game Boy Color, in the coming section. While their internal SoCs are pretty similar in most aspects, the differences of their capabilities will become significant in due time. The original Game Boy, as well as the later Game Boy Pocket and Game Boy Light, all contain within themselves the DMG CPU system on a chip, at the heart of which sits a sharp SM83 processor clocked at 4.19 MHz. This odd little processor has its mixed 8-bit 16-bit instruction set derived from both the Intel 8008 and Siloxy 80 series of CPUs. It features a 16-bit address bus, for which it can simultaneously map up to 64 KB of data, as well as an 8-bit data bus with which it retrieves and stores individual bytes of the address space. In terms of working memory, the DMG CPU SoC contains 8 KB of RAM, 8 KB of VRAM, as well as 127 bytes of high RAM for use during any direct memory access procedures. Despite its nominal clock speed of 4.19 MHz, the SM83 CPU can only execute a single memory access instruction every 4 cycles, which is why you'll often see people talk about the duration of instruction times on the Game Boy CPU in machine cycles, or M cycles. At a frequency of about 1 MHz, these M cycles divide the 4.19 MHz clock cycle or T cycle frequency of the SM83 CPU by 4. The CPU CGB SoC, which you'll find inside of the Game Boy models Color, Advance, and Advance SP, similarly also contains a SM83 CPU at its heart. To play back original Game Boy games without issue, this processor is also clocked at only 4.19 MHz per default, but setting a special register within the CPU allows us to enter its CGB mode, also called double speed mode, in which the clock frequencies of all hardware components within the SoC are doubled. Accordingly, the SM83 CPU of the CPU CGB package may also be set to execute around 3.38 million T cycles and around 2.1 million M cycles per second. Furthermore, the CPU CGB SoC also features additional memory regions which may only be addressed in CGB mode, allowing us to use up to 16 KB of VRAM and a whopping 32 KB of RAM. Now, looking at these initial memory allotments, you might be led to believe that our project to play MIDI files on an original Game Boy already has hit an impassable obstacle. After all, with only 8 KB of RAM to work with on the original DMG CPU, it appears that we're not even given enough space to store an average-sized MIDI file. Luckily though, the Game Boy was built from the ground up to not just rely on its built-in hardware for playing games, but rather to interface with different cartridges whose components, as you'll soon see, actually offer us a great deal of versatility. To address these components, the SM83's memory space reserves 32 KB to interface with the cartridge read-only memory, or ROM module, as well as another 8 KB to interface with an external RAM module, which may be read from and written to at will. While these additions in memory may not look all that game-changing on paper, two small techniques called ROM banking and RAM banking will, from here on out, provide us with essentially all the memory our MIDI parsing desires could ever need. To understand how RAM and ROM banking works, you just have to imagine a ROM or RAM chip that far exceeds the address space of our SM83 CPU. As an example, let's just imagine a cartridge with a 1 MB ROM chip for now. By dividing the 1 MB memory space of the ROM chip into many smaller 8 KB or 16 KB chunks, called banks from here on out, we can swap parts of our CPU's 32 KB ROM address space for another bank using a so-called memory bank controller or mapper chip. Although swapping out our addressable banks will temporarily cause us to lose access to the data we were previously able to read, we can still use ROM banking to slowly read out data structures far larger than 32 KB in size, one bank at a time, and extract any information we may consider relevant. The same mechanism works for the cartridge's RAM chip as well, potentially allowing us to save large swaths of data. Using a mapper chip called MBC5, essentially the fanciest Game Boy memory bank controller officially released by Nintendo, we may access a ROM chip of up to 8 MB in size by gradually reading out its 512 ROM banks of 16 KB each. Furthermore, we are given access to an external RAM chip of up to 128 KB divided into 16 RAM banks of 8 KB each. Thanks to the advanced capabilities of the MBC5 mapper, both of these memory chips also fully support the stricter timings of the Game Boy Color's double speed mode. With this much high-speed memory on our hands, our MIDI parsing project is practically guaranteed to never suffer from any RAM or ROM shortages, which means that we can now move ahead to look at another aspect of the Game Boy's hardware, the Game Link port. Now, we already know that the Game Boy's Game Link port is at least somewhat capable of MIDI throughput, since all regular MIDI interfaces use it to interface with the Game Boy. However, things sadly aren't quite that simple, and there's actually a massive difference between the Game Boy's data reception and data transmission capabilities that we need to be aware of moving forward. The reason for this large gap in capabilities that I'm about to describe is related to the clock signal that accompanies the transmission of data on the serial signal line. For each bit that is to be transmitted via the Game Link protocol, the clock pin will first have to change its state from high to low before the serial data line has assumed its new transmission potential, low when transmitting a 0, high when transmitting a 1, and then back from low to high once the data line has assumed its correct level. Only after the second clock level change will the bit be read out from the state of the serial line. Thanks to this approach, the Game Link protocol doesn't have to worry about signal timing, since the receiving Game Boy will always know when to read out its serial line simply by reading its clock state. However, as a downside, each transmitted bit will require 2 changes to the clock signal level, while a full byte of transmitted data already requires 16 such level changes. This might not seem that big of a deal to begin with, since the changing of a logical level is about the simplest operation a processing unit can perform. However, on the original DMG CPU, Nintendo has chosen to fix the frequency of the clock signal's change rate during a transmission of a data byte to 8192 Hz, at which rate we could transmit exactly 1 KB of data out via the Game Link port each second. However, this 1 KB transmission rate assumes the presence of exactly 0 functional overhead, and is therefore entirely unrealistic. More likely, you'll be struggling to send out more than a few hundred bytes each second, and that is assuming that you don't perform any handshakes with the receiver to confirm a successful transmission. In the case of MIDI, this low transmission rate is actually a rather significant problem, since the official MIDI electrical specification calls for transmission of MIDI at exactly 31,250 baud or 31.25 kHz. However, there are 2 points which can somewhat mitigate the severity of the speed discrepancy for us. The first factor to consider is that while the MIDI electrical standard does call for transmission of signals at 31.25 kHz, this doesn't automatically mean that every MIDI piece will also send out 31,250 signals every second. Instead, a MIDI parser or MIDI device will only send out as many signals as are required within a second at the specified frequency of 31,250 baud. Depending on the song, you could imagine entire seconds or even minutes passing without any signals being sent. Furthermore, the CPU CGB SoC of the Game Boy Color and its ancestors also offers us several speed modes for the clock signal, which allow us to reach a maximum frequency of 524,288 Hz or 64 KB per second, well above the MIDI requirements. Both the original DMG Game Boy as well as its later models are all capable of reading data at this frequency, meaning that we shouldn't suffer from any MIDI transmission issues when running our parser in the double speed mode of the Game Boy Color. However, while the original Game Boy models with the DMG CPU SoC are capable of reading such fast transmissions, they're not able to increase their clock speeds whatsoever. The unalterable clock frequency of 8,192 Hz easily makes for the most damning limitation of the original Game Boy hardware, as you'll later see. For now though, let's first finish out our look at the Game Boy hardware by looking at which timing functionality the SM83 CPU offers us for the purposes of playing back MIDI files. Since the correct timing of our signal parsing work is obviously a critical component of any music software application, it'd be great if we could stop and resume the execution of our MIDI parsing program with microsecond precision. However, while modern microprocessors, like the RP2040 of the Raspberry Pi Pico, run at frequencies which make such microsecond pause instructions essentially trivial, the SM83 CPU is simply too slow for such applications, and therefore also doesn't feature a similar pause instruction from the get-go. Now, the GBDK 2020 SDK, which we'll use to program the functionality of MIDI-BOI at a later stage, does in fact feature a pause instruction. But since this functionality only allows us to halt the program for time spans in the millisecond range, it is essentially unusable for our purposes. Instead, to make sure that our MIDI signals are sent out precisely on time, we'll have to work with the SM83's timer registers. Originally, these registers were meant to facilitate timer-based interrupts, which could be called at a specified frequency. But since these interrupt functions can't receive any parameters, they're not useful for our purposes either. Without any other options available to us, we will have to rely on an admittedly rather scuffed approach of using these timer registers to keep track of time. But we'll get into that topic more once we discuss the inner workings of the MIDI-BOI program. For now, we can summarize this look at the Game Boy hardware as follows. The SM83 processor of the DMG and CPU CGB SoC of the different Game Boy models is weak, but we have yet to run into a single damning limitation that directly threatens to prevent our MIDI parsing efforts. The Game Boy certainly wasn't meant to work with MIDI, and accordingly doesn't offer us any bit of convenience while we're developing such an application, but at the present moment it, at the very least, would appear as if parsing a MIDI file on the Game Boy is indeed feasible. Of course, we've reached this conclusion without looking at the MIDI file standard yet, so we don't really precisely know what technical requirements we'll need to adhere to moving forward. For us to know just how problematic some of the limitations we've learned about in this previous section really are, we'll next have to look at the MIDI 1.0 file standard, which describes the file format from which we have to read our MIDI signals. Alright, The MIDI 1.0 file standard. At this point of the video, I could reasonably talk your ear off for at least an hour or two as I rant about all the oddities which make MIDI files as beautifully efficient as they are. However, for the sake of making this video actually enjoyable to watch, I've decided to save us both the time and will only cover the most relevant specifications. So here we go. Internally, each MIDI file is made up of several separate data regions and components which carry more or less relevance for our undertaking. At the start of each MIDI file sits a header from which we can infer basic information such as the type of MIDI file we are dealing with, the time division of the song tempo, as well as the number of track chunks contained within the file. Each of these track chunks in turn contains a single track of MIDI events, made up of several MIDI signals that are to be sent out throughout the playback of a song. Oftentimes, these tracks correspond to a single channel and instrument of a MIDI file, but this isn't always the case, since you'll oftentimes have more than 16 tracks in a song file and can change the instrument of a channel through so-called program change MIDI-CC signals. To ensure that the different MIDI events of a track chunk within a MIDI file are all sent out at the correct time, they are each associated with so-called delta time or event time values. This value designates a duration of MIDI ticks that separate the playback of this event from either the start of the song, if it is the first event of a track, or otherwise from the prior event of the track. An event with an event time of 0 will always play as soon as the previous event of the track has been parsed. An event with an event time of, let's say 10, for example, will have to wait 10 MIDI ticks after the parsing of the previous track event to play. The duration of a MIDI tick, meanwhile, can be calculated through two distinct values. The first is the time division value, which is always static and can be read out from the MIDI file header. The second is a dynamic value called the tempo of a song. This tempo is always initialized with a default value of 500,000 at the start of the song, and then usually changed at the beginning of the song's first MIDI tick through a so-called set tempo meta event. Once these two values have been acquired, you can simply calculate the duration of a MIDI tick by dividing the current song tempo by the song's time division. The resulting value designates the duration of a MIDI tick in microseconds. To both allow for the precise keeping of time during the playback of a MIDI song, as well as to support long pauses within a MIDI track, the tempo, time division, MIDI tick duration, and event timing values are usually saved with a precision of up to 32-bit. Event timings can also be saved in a smaller or even larger format, but the MIDI 1.0 file standard specifically advises against using data types larger than 32-bit, since most MIDI routines will simply break when encountering variables that big. So at this point, we can already note the fact that our Game Boy MIDI parser will have to work with 32-bit data types in the coming future, even though the SM83 processor uses a mixed 8-bit and 16-bit instruction set. This lack of native 32-bit instructions on the side of the Game Boy certainly makes for a bad omen for the things to come, but isn't nearly as bad as it might sound upon first mention. It's actually fairly trivial to write routines which allow processors to work with data types larger than their instruction set would otherwise allow for, and the GBDK 2020 SDK, which MIDI-BOI will be based on, actually has implemented all the necessary functionality to natively support calculations of 32-bit data types. However, this support comes with one obvious drawback: performance. Since the 8-bit data bus of the SM83 CPU only allows us to fetch at most 1 byte of data during each M cycle, assuming no overhead for the calculations or temporary data storage, you can probably already guess some of the huge time spans that even simple 32-bit plus or minus calculations will require. The performance of 32-bit calculations on the SM83 CPU is indeed bad enough that the developers of GBDK 2020 specifically advise you to refrain from using them whenever possible, but sadly we are given no choice in the matter. Still, at this point, we at least know that our Game Boy will be able to handle all data types that a MIDI file will throw at it, which is certainly a positive sign. Of course, the performance of the needed 32-bit calculations will inevitably be a rather sizable issue, one that is made no better by the fact that MIDI files also generally use a simple form of compression to reduce their file sizes. You see, the MIDI 1.0 file standard dictates that when two MIDI events with the same status byte, let's say two note on signals for channel 1, follow directly after one another, you may save the second MIDI event without its status byte. Through this mechanism, you'll somewhat reduce the size of a MIDI file, depending on its complexity and how many such signal repetitions occur. But any MIDI parser that is tasked with reading out the included signals will obviously have its workload increased as a result. Funnily enough, in our case, this compression mechanism actually works in the complete opposite way that we would like it to. Since bank switching can easily provide us with more than enough storage space for even the most complex MIDI files, we'd much rather trade reduced workload during the later parsing work for a greater storage requirement. However, despite this compression being a built-in feature of the MIDI 1.0 file standard, we don't actually have to worry about it much, since we'll have to reformat the MIDI file contents for all following work regardless. As was previously stated, all the ROM banks of our Game Boy cartridge only have a maximum size of 16 KB, while MIDI files can reach several megabytes in their extent. So, we'll need to write a simpler program later on, which can divide a MIDI file by its track chunks and then store the track data, both event bytes and event timings, onto a single ROM bank. At that point, we'll then also be free to reverse the MIDI file compression to serve our specific needs. However, I'm getting a bit ahead of myself. For now, we can pretty much end our examination of the MIDI file standard, as it does, in fact, seem pretty likely that our Game Boy will be able to handle the data processing loads that the parsing of a MIDI file requires. So far so good. Of course, the SM83 simply being able to handle the workload doesn't necessarily mean that it'll handle it well. Since the proper parsing of a MIDI file requires us to stay within some pretty slim timing margins, there remains the overarching question of just how much the outdated hardware of the Game Boy will struggle with the processing of 32-bit data types and what sort of margins, if any at all, will be left with once all events of a single MIDI tick have been processed. To get a first estimate for the performance troubles that await, I initially built a simple test program which would use some basic MIDI parsing algorithms to parse the contents of a single MIDI test string and then send them out via the GameLink port. To say that things didn't go well at all would be an understatement. Good news first, however, the algorithms worked and the Game Boy, despite all its shortcomings, actually turned out to be capable of parsing a simple MIDI test string. Yet, the parsing of such a string took a lot more processing time than I'd anticipated. While this first parser was able to keep itself running mostly within the time constraints of this first test file, there was no way that it would do well with anything more complex than a basic single-track chunk file. It was pretty obvious from the get-go that some serious revisions to the basic MIDI parsing methodologies were needed to make the Game Boy function as a proper MIDI parsing device. Of course, just previously, I already mentioned some possible improvements to the MIDI file standards that could possibly grant us much-needed performance boosts, but solely pre-parsing the MIDI file to remove its compression wasn't quite enough to net us a perfect MIDI file playback, although it certainly helped the program's performance a fair bit. In the end, I had to incorporate all sorts of little tricks to get my hand on every single CPU cycle that could easily be freed without negatively affecting the playback performance. The end product of this massive performance drive was a two-part software suite made up of the MIDI file pre-parser MIDI-Dumper-GB as well as the Game Boy MIDI player MIDI-BOI. In the next section, we'll take a look at how these two components work in sync to allow our Game Boy to achieve the seemingly impossible task of playing back even complex MIDI files at full speed. Okay, welcome to Andre's tutorial for using MIDI-BOI and MIDI-Dumper-GB. As you can see, I've gone pretty old school for this one. You can put on 009 Sound System Dreamscape's trance on in the background to get you into the mood if you want to. Otherwise, why don't we just get started? To use MIDI-Dumper and MIDI-BOI, you'll need exactly 4 components, as you can see. You'll need a MIDI file, of course. First of all, you can use pretty much whichever MIDI file you want to. And then you'll need GBDK, or the Game Boy Development Kit, and MIDI-BOI and MIDI-Dumper-GB. You can get those 3 components simply by going to their GitHub repositories. You can get MIDI-BOI on my GitHub repository, also linked in the description down below. I haven't done a release version of it yet, so you can simply go to code up here, download a zip, and then save it in whichever folder you want to use. Same for MIDI-Dumper-GB, also just go to code, download zip, and there you go. Finally, we'll need GBDK, and for getting GBDK, they actually do release versions, so you can go down here to releases, then just go to the newest release, and then in the assets section here, depending on which OS you use, you can just use your version. So I'm on a Windows 64 machine. If you're on Mac OS or Mac OS ARM, or Linux ARM, use the other versions. Doesn't really matter. Okay. Once you have all of this stuff downloaded, we'll start with MIDI-Dumper right away. So MIDI-Dumper is pretty easy to use except for one component. But for now we can just do extract MIDI-Dumper here. Of course you can use 7-zip WinRAR, whichever version you want to unextract those zips. Then you can go into the MIDI-Dumper folder, and we'll actually take our MIDI file with us. So just Control-X, Control-V, so that we have our MIDI file here. Okay, this is where things get a bit complicated to start off of, because right here you have the MIDI-Dumper executable. But this is a Linux executable, which isn't actually a problem. If you're on Linux, of course, you'll pretty much know what to do right away. If you're on Windows, though, what you'll need to do now is install the Windows subsystem, or the Windows subsystem for Linux. If you just search for Windows subsystem for Linux in Google, you'll probably get into this page from Microsoft really easily, which tells you, well, how to install Linux on Windows with WSL. And here it essentially tells you what to do. Tells you to open PowerShell. So just open a PowerShell window, probably as administrator. Yep. So by right-clicking it and then open it as administrator, and then just typing WSL ---- install. I'm not going to do it because I already have the subsystem installed, but this is all you'll have to do. Okay, maybe there's some other stuff that comes up, but just basically follow this page. It's pretty straightforward. And then you'll have the Windows subsystem for Linux installed, meaning you can use Linux and Linux commands, Linux executables on Windows. To do so, you'll go into a folder that has a Linux executable like this one, and you'll select nothing in this folder, hold Shift, right-click, open Linux shell here. That'll open a Linux Windows, which looks like this. Maybe there's some more stuff that on the first time you start a shell, there's maybe more text, but essentially it looks like the Windows command line. Now, I have a MIDI-Dump executable pre-compiled in this folder. It should work with the default Ubuntu version, which is installed if you simply use this WSL ---- install version. So if you're lucky, in this folder, you can just use /MIDI-Dump and then the name of your file. So this is the exact command which should extract your MIDI file into the track and the other files that we'll need later. However, should this command, as it's written right here, of course you need to replace this last section here with your with the name of your MIDI file, obviously. But should this command for some reason not work, then you'll need to recompile MIDI-Dumper, which is pretty easy to do. You'll need CMake. So if this is your first time using Linux on Windows or using Linux in general, then you'll need to type sudo apt install CMake. CMake, that's how you write it. Then I'll ask for your password, which you're not going to get. And boop, I'm going to quit out of this, but it's essentially going to download stuff. It might ask you for a confirm prompt with Y or N as options. Just type Y and then enter again, and then it'll install CMake. Once CMake is installed, again, could be that you need to close the console and then reopen it again. So again, just go into this folder, shift click, open Linux shell here, and then CMake should work. And once CMake is installed on your Windows install, you have to type, where is it? There. CMake dot and then make. And I can do it in this folder because it should just work. And then you've built a new MIDI dump file, which is specifically built on for your system. So at that point, it is guaranteed to work. And now that we have this new executable, we can just use this MIDI dump command, type it here. And there you go. If you go into this folder now, you can see, okay, we've created all the track files that we'll need later on. And that's it. That's all you need to do for getting the track files that MIDI-Dumper will need in just a second. You can see you'll get a basic information about what MIDI-Dumper is doing with your file. Some tracks are small enough that it'll just parse them in a single file. Some tracks need to be split into separate files, or multiple files rather. But we'll get into that, what that exactly means later on. For now, you're pretty much done. Whenever you want to use a new MIDI file, you can just run this command again. Even after you needed to use CMake the first time, you'll never need to use CMake again, essentially. And you can always just run this command, obviously, then with the name of a different MIDI file. And MIDI-Dumper also already takes care of deleting the old files, so you can always be assured, as you can see there, it deleted the old files and gave you the new ones. Okay, so far so easy. Obviously, like I said, you need the MIDI file in this folder for it to find it. That's it. So this takes care of essentially the easiest part. Now it gets a bit more complex. Now we need to set up GBDK. So you have the GBDK zip file in this folder here. Again, you can just do extract here. And now you have GBDK. Now we need to be very specific about how we do this. At least if you want to have the easiest experience of using MIDI-BOI that you can have. So you can see that there's a bin folder here. This bin folder is going to be very important to us in just a second. For now, in this folder, so in the GBDK folder, which also has the bin folder, what you should do is right-click, new folder, and essentially you can name this folder whatever you want. I'm just going to name it projects, but the name of this folder doesn't matter. Then we're going to go back out. We're going to take the MIDI-BOI zip file, go back into GBDK, go into our new folder, put it here, and then right-click, extract here. And now you have MIDI-BOI main here. So MIDI-BOI should be, or rather, this should be two folders below the GBDK folder. So exactly, see, first folder projects, and then the second folder MIDI-BOI main. The reason why this is important is because we need GBDK to compile the MIDI-BOI-GB file, so the MIDI-BOI ROM file that works exactly with your MIDI file. Okay, well, I need to re-record this section because the GBDK devs broke something. So let's get back to this. Let's go into MIDI-Dumper-GB. We select all of our track files, Control-C, go back out, GBDK, projects, MIDI-BOI main. Here we go into the song files folder, Control-A to select them all, delete to remove them all, Control-V to put your new song files in, and now you've basically got everything set up. Except for two things. First of all, here in the main.c file in this folder, we need to talk about the consolidation factor. If you just open it, or let me use the regular edit file, notepad. If you check in this file, if you look around a bit, you'll find a line that looks like this, uint consolidation equals 12. If you've just downloaded the MIDI-BOI main repository and extracted it. Before you do anything, you should change this to 1 preferably. We'll talk more about consolidation in a second, but to begin with, consolidation of 1 should always at least result in a playback. Not necessarily full speed, but at least the file should play. Then we can close back out of here, and now we need to compile the MIDI-BOI ROM file. Now, earlier in the previous recording you won't get to see, I was trying to use this compile batch file. if you look in here, it basically calls the lcc.exe that we need to run, that we need to compile our .c files in here and the song files. And it does so by, if you've never used commands like this before, use the call command, and then this double period here means a folder up. So if you've set it up like me, you don't actually need to change anything here. You go a folder up to the projects folder, then another folder up to the GBDK folder, then bin and LCC. If you go in bin, and here's LCC. So this just points to the exe, and the rest should work as a command to basically compile our project. Now, it should, but it doesn't, because apparently, so if I take all of this, then open a command line in this folder, and just copy this command into here, you'll see you can't find wildcard C and no wildcard song files. Apparently the GBDK devs, either the GBDK or LCC devs, have broken something in the new version of GBDK that wildcards don't work anymore. If you let me go into another folder which I've created in an older repository which uses an older version of GBDK, and do the same thing here, and I open a CMD shell and then type the command in here, press enter, you'll see it compiles just fine. But it doesn't do so on the new version because apparently wildcards are just broken, which is cool. Not that big of a bother for us though, because you already had to set up CMake and Windows Linux subsystem for this. So you can just do shift right click, open Linux shell here. And then just, if you have CMake installed, just type make, and now it compiles your new MIDI-BOI file. This will take a second, but it'll give you this warning. Just ignore it. This is just bad programming on my side. And eventually it'll create all of this stuff. There should be no error here. If there is an error, just let me know in the comments or through the GitHub repository. But I've set it up that really there shouldn't be any errors here. If there are, then I've messed something up and the program needs to be changed. But you'll see all the thingies getting compiled, and then this is the ROM banking, which we'll talk about in a second. And with that, you have your new MIDI-BOI-GB file, and everything is ready to run. Except for one big thing, which is the consolidation factor, which might make it so that your program doesn't run at full speed, or your MIDI-BOI ROM doesn't run at full speed. And to understand how you can fix that, how you can get your file to run at full speed, and what exactly consolidation even is, I'll need to now explain how MIDI-BOI works code-wise and what actually the output of MIDI-Dumper-GB is. And for that, we'll switch over to VS Code. Welcome to VS Code. As you can see, I've got the MIDI-BOI folder open right here. We're currently in the track descriptor.h file, which is the first file generated by MIDI-Dumper-GB. And I was thinking about how exactly I'm going to explain all the output files of MIDI-Dumper-GB, as well as the way MIDI-BOI works. After all, the entire topic is pretty complex, but then I realized, wait a minute, I wrote a master's degree on this topic. So actually, why don't you just sit back, relax, and let me read from my own master's degree about how MIDI-Dumper-GB and how MIDI-BOI work. (7.1) MIDI-Dumper-GB. This 7th chapter will now deal with the development of a two-component system for playing MIDI files on the Nintendo Game Boy. First, we will introduce the software MIDI-Dumper-GB, whose main purpose is to decode and save all the relevant contents of a MIDI file. The ultimate goal of MIDI-Dumper-GB is, of course, to create various modular files that can dynamically be read by our MIDI-BOI software on the Game Boy at a later point. However, due to the limitations of the DMG hardware discussed above, we are already aware that all contents of these files must somehow be distributed across various ROM banks of 16 KB each. For this purpose, we will use a compilation process called autobanking. As an integral part of the GBDK 2020 SDK, autobanking will thankfully save us the manual distribution of the given MIDI data to the various ROM banks of MIDI-BOI, but only under certain restrictions. The most important point of note here is that autobanking only works with data types and constructs of the programming language C. Furthermore, these data types may not be arbitrarily formatted, but the contents of each bank must be declared in a header file and separately defined in a C file. During the creation of both of these files, a strict adherence to the formatting templates of the GBDK 2020 documentation forms the precondition for the proper execution of the automatic data distribution algorithms. To ensure that the output data from MIDI-Dumper-GB is compatible with the autobanking tool, it must be saved as fields and arrays dispersed across multiple C files. First, however, we'll need to extract all required data from within a MIDI file. At this stage, a GitHub project mentioned earlier can help us with this first part of the formatting process, MIDI parser. The original version of MIDI parser consists of two different components, each with a purpose of its own. The file MIDI-parser.c consists of those functions and definitions that enable a sequential decoding of a MIDI file, starting at its header and then moving through the different tracks. According to the project description, this core part of MIDI parser is intended as a library that can freely be integrated into various MIDI projects by the user. The second part of the MIDI parser project, a file called MIDI-Dump-C, shows us what such an integration might look like. After compiling the MIDI parser project, MIDI-Dump.c is built into a Linux executable, which accepts a MIDI file, decodes it using the functions from MIDI-parser.c, and finally outputs the contained MIDI events as strings in a terminal. Due to all these predefined functionalities of the MIDI parser project, a modification of the MIDI-Dump.c file turned out to be all that was necessary to create a program which generates several header and C files, all pre-formatted for autobanking as required by the GBDK 2020 SDK, and then fills them with all the relevant contents of a MIDI file. However, the considerable amount of conversion work that needed to be carried out to achieve this capability makes an overview of the performed code changes very much unreasonable. So, starting with the files trackdescriptor.h and trackdescriptor.c, the following section will instead focus on explaining the output files of MIDI-Dumper-GB, since they are by far the most important components of the MIDI-BOI project. However, if desired, the entire code of MIDI-Dumper-GB can also be viewed at your discretion on its GitHub repository. Figure 30 above shows the entire structure of the track descriptor header file. After the successful translation of any given MIDI file, this header will always look the same and will always consist of the following components. Its first line includes the platform library of the GBDK 2020 SDK, which provides us with all the code frameworks required for the autobanking of all following data structures. Probably the most important of these frameworks for using multiple ROM banks is a function called bankref, or bankref_extern for external data types. Its purpose can be explained as follows. When using the bankref statement, a reference to the number of the ROM bank containing a variable or function is created during compilation of the program code. As will be shown later, the name of a variable or function with a stored bankref can then be used at a later point as the target value of another statement, which allows the corresponding ROM bank to be loaded into the visible address space of the Game Boy's SM83 CPU. Thanks to this bankref system, it is not necessary for us to know explicitly, at the time of our programming work, what ROM bank the address data will later be stored on, which is why the actual distribution of all static values can be left to the compiler itself. This is also the great advantage of the autobanking method, since it completely eliminates the need for any manual distribution of the program's data thanks to the bankref system. In order to use the capabilities of autobanking, a corresponding bankref_extern reference is generated in the track descriptor header file for each declared external variable. Specifically, these variables are a uint16t value total tracks, which specifies the number of MIDI tracks either read directly from the MIDI file or newly split off by MIDI-Dumper-GB, a uint16t value time division, which specifies the time division value that was read from the MIDI file header, a uint32t value last event time, which contains the absolute event time of the last MIDI event. This variable is used later on to formulate a highly time-efficient termination condition for the main MIDI playback loop of MIDI-BOI. And finally, the track descriptor header also contains a uint16T array track sizes, which specifies the number of MIDI bytes contained in each decoded track. All these values are then defined in the corresponding track descriptor.c file. Figure 31 shows us an example of how this construct may be filled. In addition to defining our variables, track descriptor.c also uses the instruction pragma-bank255 to tell GBDK 2020's compiler that all subsequent data in this file should automatically be distributed across the banks of the ROM chip. This distribution of variables across the different ROM banks then also gives the various bank ref references defined here their required values during the build process of the final ROM file. As can be seen from the above example code for filling the track sizes array, the size of a single MIDI track has been limited to a maximum of 6,144 bytes. This restriction was implemented by allowing MIDI-Dumper-GB to automatically create a new MIDI track once the number of MIDI event data bytes read from a single track exceeds 6 KB. The newly split off track, as well as its two corresponding files, will then hold the next 6 KB of MIDI event data and 8+ KB of event timings of the track. This ensures that the MIDI events and event timings of a track, plus any potential overhead for the data types, will always fit together on a single 16 KB ROM bank. Once MIDI-Dumper-GB has stored all the data for describing our MIDI file in the track descriptor construct, two additional files called trackfunctions.h and trackfunctions.c are automatically generated next. These contain the most important functions for working with the following MIDI track data and are structured as follows. As can be seen directly from the screenshot of the track functions header file in figure 32, this construct is an essential data area that will not be distributed across the banks of the ROM chip moving forward. Instead, the contents of these two constructs, together with the MIDI-BOI program code explained in the next chapter, are written to the first 16 KB of the ROM file, which remains permanently addressable and thus permanently usable by our Game Boy. For this reason, no declarations of bank ref references are necessary at this point. Instead, all required functions can regularly be declared as external types. The exact purposes of these given functions can be inferred from their definitions in the trackfunctions.c file, but their precise makeup will differ somewhat depending on the number of MIDI tracks contained within a song. The trackfunctions.c file, filled with the data of the MIDI file cavestory.mid, as shown in figure 33, is therefore only an example to illustrate how this data construct generally works. As can be seen in the screenshot of figure 33, the tasks of trackfunctions.c are relatively complex and multi-layered. First of all, the platform tools of the GBDK 2020 SDK are included again, so that different ROM banks may be used in this construct moving forward. However, the goal at this point is not to distribute the data from the trackfunctions.c file to different banks, but to offer several functions through which the ROM banks of the various MIDI track data arrays can be loaded into the addressable memory space of the Game Boy. For this reason, all track header files generated by MIDI-Dumper-GB are included at the start of this file. Additionally, a bank ref value is declared for each of these header files, which later provides us a reference to the ROM bank number of the header data ROM bank. Next, a first function that can load a ROM bank containing the MIDI events of a track into our addressable space is defined. This function is called switchbanksData and getPointer and behaves as follows. First, a uint8t value is passed to the function, which is usually derived from the track number that we're presently parsing. Based on the values passed, a switch statement loads the memory bank associated with the event data of a track through the MBC chip of the game module into the upper 16 KB of switchable ROM address space. Once this operation has concluded, the address of the first value of the now visible MIDI event array is returned. The remaining three functions in the trackfunctions.c file are very similar to this first function in terms of their structure. For example, the switchbank's event timings and getPointer function basically implements the exact same mechanism for loading the ROM bank of an event timing array. The only major difference to the above function is the return value, which must of course correspond to the larger uint32t data type of the event timings array. The functions justSwitchBanksData and justSwitchBanksEventTimings also contain the exact same two switch statements for switching ROM banks, but do not return any values. Since the transfer and return of function values is a rather time-consuming process on the Game Boy CPU, these two functions can achieve better performance when switching banks in all those cases where the array start location of the data to be addressed is already known to us. Now, at this point, we've already discussed the event and timing data of the various MIDI track files at length, which is why these last output structures of MIDI-Dumper-GB will now be explained as well. Since MIDI files can essentially contain any number of MIDI tracks, meaning that different numbers of these track files are created depending on the file contents, all the created track files are named according to the pattern track_.h and track_.c, with the underscore being replaced by the number of a track, starting with 0. Obviously, the actual structure of all track header and track C files is always the same, regardless of the translated MIDI file, since all variances in content are solely expressed by the data arrays containing different values. Accordingly, it will suffice at this point to show the converted files of a single track to illustrate the underlying mechanisms. Due to its small size, the 10th translated MIDI track of the file carnivale.mid was chosen for presentation in this specific case. As can be seen in the image above, our track header file declares only two arrays. More specifically, these are an unsigned char array called track10data, which contains all message bytes of the MIDI track, and a uint32t array called track10event-timings, which contains the timing offsets of all events. Once again, the data from the C file is distributed to the various banks of the ROM chip, which is why different bank ref values must be declared within all track files for both arrays that they contain. The C file associated with this header is shown in figure 35. As can be seen from the screenshot of track10.c in figure 35, this file simply handles the definition of all values that were read from the corresponding track by our MIDI-Dumper-GB project. The MIDI events are specified in individual hexadecimal bytes, while the event timings are defined as simple uint32t decimal values. However, a closer inspection of the stored array values reveals two small peculiarities that serve to reduce the computing time of the following Game Boy program and should be known for complete understanding of the MIDI-BOI code that will be presented later on. First, you may note that the track data array contains a byte with the value of OXFF at its end. However, this byte was not taken from the contents of the original MIDI file, but rather added by MIDI-Dumper-GB as a signature to mark the end of this array. The way MIDI-Dumper-GB works guarantees that this byte is always located at the position of a status byte. However, since the MIDI standard does not define a MIDI event of the type OXFO, our later program can interpret the reading of an OXFF status byte as it having reached the last MIDI event of a track. This mechanism allows us to avoid some computationally expensive comparisons with those previously shown 16-bit track size variables in some performance-critical segments. Similarly, it should be noted that the associated event timings are also stored in a non-standard format within the track event timings array, again because of performance reasons. While the original MIDI standard calls for the use of relative timing offsets, which designate the amount of time that is to pass in between two subsequent events, MIDI-Dumper-GB instead stores all timings as absolute time values, which designate the number of MIDI ticks that need to have passed since the start of the song's playback until an event is played. This means that the stored values are much larger and that the maximum song length is now constrained to only containing as many MIDI ticks as can be stored in a uint32t variable. But as the next chapter will prove, this change ends up making the process of timekeeping on the Game Boy much simpler and, critically, way more efficient. But regardless of these two small changes, all MIDI tracks within a MIDI file are translated according to the exact same pattern shown in figures 34 and 35 above. Since no data relevant to our purposes can be extracted from the contents of a MIDI file after all tracks have been converted, this discussion of the various output data of MIDI-Dumper-GB can now be concluded. Before playing the data converted here for the first time, this work now only needs to focus its attention on the MIDI-BOI software, which implements the necessary procedures on the handheld hardware. Chapter 7.2 MIDI-BOI. Now we have finally reached the topic of playing back the MIDI data encrypted by MIDI-Dumper-GB. From the information in all previous chapters, it should already be apparent that a significant deviation from conventional MIDI playback procedures will be necessary to implement the required mechanisms with sufficient performance as to allow the full-speed parsing of MIDI files on the SM83 CPU. Accordingly, this chapter will deal with the developed code parts and procedures in much greater detail than all previous chapters, although for the sake of brevity we will refrain from listing trivial details in some places. As in all previous discussion of the developed programs, the code presented here can also be viewed in more detail in the directory on the GitHub website according to your own needs. To begin with, our MIDI-BOI project must, of course, first include all header files relevant to this Game Boy program, as well as the necessary GBDK 2020 libraries. For our purposes, the GBDK 2020 platform libraries for the Game Boy and Game Boy Color are particularly important as they give us access to the registers and functionalities of the SM83 CPUs of both devices. Since GBDK 2020 only allows for the programming with integer and boolean variables, only the standard libraries standard int and standard bool, as well as the library standard lib.h, which provides us with those memory allocation functions required later on, need to be included in order to use all data types of this project. Two additional include statements allow for the decrypted data from our MIDI file to be added to the project. Since all generated track files were previously included in trackfunctions.h, only this header file and the file trackDescriptor.h need to be explicitly specified for the later use. And since trackDescriptor.h is also a construct placed on an unknown ROM bank, a bankref extern reference value should also be declared for it. Now we can start running through the developed program code step by step. For simplicity, the following analysis starts with the main function, which is the entry point of the program. As shown in figure 37 above, the structure of the main function is relatively compact and simple. To begin with, several setBKG functions are called, which set up the static background image which contains my logo and the controls of MIDI-BOI. This image will then be displayed once the show BKG and display on instructions are executed. Since our software does not want to receive data, use input interrupts, or draw any dynamic sprites, all interrupt calls of the Game Boy can now be disabled right away by using the setInterrupts function and passing to it a value of 0x00. Many of the Game Boy's features that are otherwise critical to its gaming experience will hereby stop working as soon as the program starts, but they all are unnecessary for the playback of a MIDI file. In addition to disabling all interrupts, the Game Boy's audio processing unit may also be shut down by passing a value of 0 to the CPU register NR52, Audio Master Control. Without the audio hardware running and wasting energy, the handheld's battery life will be massively boosted during the execution of the following MIDI-BOI code. Now we can finally enter the main loop of MIDI-BOI, which is executed perpetually until the handheld is shut off. In this loop, MIDI-BOI will first wait until the user presses down on the A button, and then enter the play pre-parse track function, which is where the actual MIDI parsing work will now take place. The first code lines from play pre-parse tracks shown in figure 38 illustrate how variables located on the various ROM banks of the game module are to be used moving forward. Before you can access the distributed information, you must first call the MBC chip with a switch ROM statement and then load the ROM segment containing the relevant data into the visible memory space of the Game Boy. Only then can the corresponding values be read correctly by our program. At this point, there are several ways for us to work with the values of the cartridge's ROM module. In the screenshot above, figure 38, for example, the ROM variable total tracks is copied to a new const variable in the Game Boy's RAM so that the corresponding bank of the ROM chip does not have to be loaded before each access to this value. When using banked values that are read frequently, such as the number of tracks in a MIDI file, this redundant storage method can significantly improve the performance of a banked program. Due to the, for our purposes, generous memory allotments of the DMG hardware, MIDI-BOI is not limited to just storing individual ROM values into the Game Boy's RAM either. Accordingly, the next few lines of the play pre-parse tracks function deal with the definition of various large arrays, which are intended to provide us with constant access to some of the most important data for playing back MIDI tracks. First, an array called all track sizes is created, which is obviously meant to indicate the number of MIDI bytes contained in each MIDI track that is to be played. Analogous to the previous definition of total tracks, the data from the ROM array track sizes is simply copied to RAM after a switch ROM call. Across the next few lines, we then define two different pointer arrays which always point to the currently relevant address positions within the MIDI event and event timing arrays during the playback of the different MIDI tracks. By using the auxiliary functions switchbangs event timings and getPointer and switchbangs data and getPointer from the track functions.c file, the address positions of the first data values of all arrays stored on the cartridge's ROM may be obtained within an initialization loop and then stored as start values for the different pointer positions. This approach obviously makes particular use of the fact that all values of the various data arrays are stored in read-only memory, which means that they cannot be changed during the runtime of the program. Once they are written to the ROM chip by a flash cartridge software, their locations become unalterable. Logically, this also guarantees that the address values of the first bytes of all arrays always sit at the same positions, which is why it's only necessary to store all relevant address values once in two different arrays at this point. Of course, these address positions are retained even after the temporary loss of access due to a switching to another ROM bank, since all address locations are restored when the relevant bank is once more loaded into the address space later on. Therefore, only the simpler just switchbangs data and just switchbangs event timings functions need to be used for reading the data arrays henceforth. And this significantly improves the performance of our program, especially due to the aforementioned time requirements when passing and returning function values on the SM83 CPU. However, in order for this performance gain to truly be realized, another special feature of the Game Boy CPU must be taken into account at this point. According to numerous tests on the Game Boy debugger Emulicious, the use of arrays to store all address values is generally noticeably less efficient than the use of constantly redefined singular pointers if the data contained in the pointer array is accessed via a second index. So if these two address arrays are used like 2D arrays, which only store the starting positions of all arrays and allow access to the following bytes via a second index, the code execution times for retrieving the contained data deteriorate significantly on our Game Boy. For this reason, access to the array data should only ever take place via an iteration of the address pointer, followed by a dereferencing operation. This recommendation is taken directly from the documentation of the GBDK 2020 SDK, which argues in its coding guidelines chapter that for accessing data within an array, continuously iterating a pointer is significantly more efficient than using indices. After the above pointer arrays have been initialized with the array addresses of all tracks, a final step in the given code snippet defines a Boolean array called TracksUnfinished, which, as its name suggests, uses a Boolean value to indicate for each track whether all its MIDI events have already been played. When initializing this array, it is sufficient to check the all track sizes array to see whether the corresponding tracks contains any MIDI events to begin with. Next, we define some important variables whose assigned values must differ depending on whether the program is to run on a DMG CPU or a CPU CGB SoC. The first of these is a variable called clock frequency, which stores the iteration speed of the TIM-A register used for timekeeping. As already mentioned in a previous chapter, its most useful incrementation rate for our purposes sits at 16,384 Hz on the original Game Boy, or 32,768 Hz while we're in the Game Boy Color CGB mode. Since the use of CGB mode is desirable for our purposes, mainly due to the associated performance increase when transferring those MIDI bytes that will be parsed in the following sections, the value of clock frequency must therefore vary depending on the hardware executing this code. For similar reasons, activating CGB mode will also require a redefinition of the next two values. The first is a variable called Consolidation, which defines how many MIDI ticks are to be combined into a single pass of the subsequent for loop. This approach of bundling several MIDI ticks into a single program tick can massively boost the performance of the following program, since many MIDI files have a much higher sampling rate during playback than is actually necessary for the correct playback of a song. For example, the shortest time interval between the playback of two consecutive MIDI events within the file cavestory.mid, which was used as a first test file for the development of MIDI-BOI, is 96. All larger delta times in the file can also be divided cleanly by the factor 96. Which means that all MIDI parsing programs would invariably perform all the necessary calculations to evaluate 95 empty time steps between each time a single MIDI tick containing an event is to be played, despite the fact that nothing will ever actually happen in these empty ticks. The consolidation variable of MIDI-BOI therefore compresses several MIDI ticks into a single program tick, so that the unnecessary computing effort when playing back a song is reduced as much as possible. However, care must be taken not to choose a too large value for this variable, since, as already mentioned above, timekeeping on the Game Boy is done by a counter register, which is incremented at a frequency of 16,384 Hz on the DMG CPU and at a frequency of 32,768 Hz on the CPU CGB. Since the maximum value of this 8-bit timer register is OXFF, or 255, a program tick must not be longer than 254 times the increment duration of TIM-A, otherwise the algorithm for timekeeping presented below would no longer work correctly. On the original Game Boy, the maximum duration of a program tick would therefore be approximately 15,500 microseconds long, and on the Game Boy Color in CGB mode hold a length of approximately 7,751 microseconds. Accordingly, the consolidation factor on the Game Boy Color when using double speed mode should also never exceed more than half of a consolidation value that works on the original Game Boy. Next, a wait tick between sense values introduced, which specifies the wait time after the successful transmission of a MIDI byte in increments or ticks of the TIM-A register. According to the comments in Arduino Boy's source code, you should always wait about 500 microseconds after sending a MIDI byte to give the MGB software enough time to process a newly transmitted MIDI signal. However, with the total time overhead associated with sending MIDI bytes on the original Game Boy hardware, a wait time of at least 18 TIM-A ticks, or 1098 microseconds, turned out to be necessary for the transmission process to run smoothly on the DMG CPU. However, since the Game Boy Color is much faster at sending bytes, it only has to wait 20 TIM-A ticks, or about 610 microseconds, in CGB mode with its register iteration rate doubled. Once all these variables have been defined, an if query uses the GBDK2020 internal term_CPU to query the CPU type on which the MIDI-BOI software is currently running. If this value has the value OX11, internally defined as CGB type, we know that our code is running on the Game Boy Color CPU, which is why the previously indicated changes to the variables ought to be executed. First, however, the CGB mode is activated via a call of the CPU fast function. Only then is the iteration rate of the TIM-A register set to 32,768 Hz, the wait time after sending a MIDI byte reduced to 20 double-speed TIM-A ticks, and the consolidation value halved. Using all the values defined above, the following section of code can now finally focus on the initial timing calculations for the subsequent MIDI playback. The initial speed of the MIDI song is calculated in advance using the time division value, which has already been extracted from the header of the MIDI file by MIDI-Dumper-GB. To read the stored value from the cartridge ROM, a switch ROM call is used, after which we store the banked value in a new RAM variable called timediv. At the start of a MIDI song's playback, its initial tempo value is always defined at 500,000, and may only be changed thereafter through a special sendTempo meta event. However, since such meta events, like all other MIDI events, are only played at a set point in time, defined by an associated MIDI event timing value during the playback of the song, the timekeeping mechanism should always be pre-initialized using the standard tempo value, which holds until the first set tempo meta event is parsed by our program. To do so, the number of TIM-A register ticks, which corresponds as closely as possible to the duration of a MIDI tick, must be calculated. As a first step in this process, you might think that the microsecond duration of a single MIDI tick should now be calculated by dividing the tempo value by the time division value. Yet, at this stage, another small problem of the Game Boy hardware rears its head. Since the SM83 CPU does not contain processor instructions for floating point calculations, the GBDK2020 SDK also does not offer any floating point data types with which the following timer values can be calculated accurately to the precision of the decimal places. By default, we do at least have access to a two-part data type called fixed, whose upper and lower bytes can be used separately for calculations of the decimal places, but for our purposes of achieving the most accurate timekeeping possible, its two 8-bit values are unfortunately not precise enough. Thus, in order to perform the following math as accurately as possible, all calculations have been redefined at this point so that the largest possible values are always derived in each step. Theoretically, the absence of decimal places in these larger intermediate values should have less of an impact on the final result. So, to derive the largest value possible from our calculation of the MIDI tick duration, our stored time division value is first divided by the number of consolidations per program tick. Afterwards, the variable tick duration no longer gives us the microsecond duration of a single MIDI tick, but rather the duration of a longer consolidated program tick. Now, the duration of a program tick should be converted as accurately as possible into a Hertz value. To do this, it would essentially suffice to divide 1 million microseconds by the duration of a tick, but the resulting frequency values are usually small enough that rounding errors inevitably have a significant effect at this point. For this reason, despite our lack of floating point data types, the first decimal place of the Hertz value must be calculated. To do so, a second frequency value is calculated, which divides a duration of 10 million microseconds. In a next step, this first decimal place of the above calculation can be obtained by a modulus operation against the value 10. If this remainder should turn out to be greater than 4, the previously calculated Hertz value is rounded up by an addition of 1. Finally, the rounded frequency values can be used to determine the number of TIM-A ticks that correspond to the duration of a program tick. Simply divide the counter frequency of the TIM-A register by the Hertz value and store the result of this calculation in the variable needed increments. In the next code section, the previously mentioned value last event time from the track descriptor.c file comes into play. As was explained in the last chapter, it will serve as a termination condition for the playback of the MIDI file by designating the last MIDI tick which contains a MIDI event that is to be parsed. Given the critical role this value therefore plays moving forward, constantly changing the ROM banks to read it out would also be undesirable, which is why another constant RAM variable called song finish time that stores a value derived from last event time is defined here. The calculations used for the determination of song finish time, as shown in the screenshot above, serve the following purpose. Since a consolidation value has previously been introduced, which in a worst case scenario might not evenly divide the last event time of a MIDI song and thus prevent the playback loop from terminating correctly, a modulus operation is used to determine the remainder of last event time after its division by the consolidation factor. Additionally, in order to make it easier for us to formulate an abort condition later on, the value of song finish time should not represent the time value of the last program tick containing a MIDI event, but rather the first tick value after all events have been played. Therefore, the previously determined remainder is subtracted from our consolidation value, and the result of this calculation is then added onto last event time. After saving the end result of this calculation, the song finish variable now defines the program tick at which the subsequent playback loop must be exited to avoid any potential incorrect data reads. Within the following code snippet, the play pre-parse tracks function now defines several variables that do not strictly need to be made available before a playback begins, yet are declared and assigned default values before entering the playback loop rather than within it, simply for performance reasons. For simplicity's sake, the explanation of the values has elapsed time limit, message type, timer quotient, joy state, and song pause time will be postponed until we reach the relevant code sections later on, which is why only the variables I and timer need to be introduced here. Intuitively, I is simply an iterator that is repeatedly incremented within the following for loop, and the timer variable does nothing but count the number of MIDI ticks that have passed since the start of the song's playback. With that, all the preparatory work before the start of the main playback loop has now been completed, meaning that the time has come for us to finally parse our translated MIDI file. Just before we enter the for loop, however, the tag register should first be set to the value 0x07, so that the TIM-A register will now be incremented at the frequencies defined above. In addition, the TM-A register is set to the value 0x00 to ensure that the TIM-A register always resets itself back to 0 after reaching its maximum value of 0xFF. As the code snippet in figure 44 shows us, the actual playback of our MIDI file takes place within a while loop, which ahead of each program tick checks whether the current timer value matches the calculated song finish time. Should this be the case, then all MIDI events of all tracks have successfully been parsed, meaning that we should exit the loop immediately to avoid creating any incorrect data output. However, as long as the value of timer is less than song finish time, there are still MIDI events remaining in our file. In this case, a for loop is used to iterate the I variable through all tracks of the song. For each of these tracks, the track's unfinished array is used to specifically check whether it still contains any remaining unparsed MIDI events. Should a track indeed still contain any unparsed events, then the just_switch_banks event timings function first loads the ROM bank containing the event timing array relevant to the current track into the Game Boy's addressable memory space. An if statement is then used to check whether the track in question really holds any MIDI events that are to be parsed during this present program tick. Since MIDI-Dumper-GB has converted all timing offsets into absolute time values starting from the beginning of the song, it is sufficient to simply check whether the timer value matches the currently relevant event timing value of the track. If the two values are indeed the same, then at least one MIDI event of the track must be played during the current program tick. To handle the event parsing work, a do-while loop is entered, which sends out, within this program tick, all MIDI events of the presently observed track whose event timings match the current value of the timer variable. In a first step within this do-while loop, a call to the just_switch_banks data function loads the ROM bank containing the now relevant track data array into the visible address space of our CPU. Then, the first MIDI byte of the now observed MIDI event is stored in the message type variable. Since a later part of the loop's code ensures that the data and timing pointers of both pointer arrays always point to the presently relevant addresses within the ROM event timing or event data arrays, this can be done simply by dereferencing the event data pointers array pointer. However, an AND OXFO operation is used at this point so that we only store the first 4 bits of this first data byte, which define the type of the current MIDI message. Since MGB can still corrupt its own working memory by processing unknown MIDI signals, and since our program shouldn't spend too much computing time on dealing with such useless or potentially even harmful signal types, only 3 different MIDI event types are specifically handled by MIDI-BOI at this point. By ignoring all remaining signal types, a significant improvement in playback speed can oftentimes be achieved, especially on the DMG CPU and when processing larger MIDI files. An initial if query therefore checks whether the current MIDI event is a node on signal with the value of 0x90 or a node off signal with the value 0x80. If one of these two conditions is met, then the current MIDI event defines a node signal that can freely be sent to MGB without us having to worry. The subsequent process for sending out all 3 bytes of the MIDI node message always follows the same sequence of instructions. First, a data byte is loaded into the SB register, serial transfer data, by dereferencing the event data pointer of a track. All bits within the 8-bit SB register are sent out via the serial out pin of the game link socket in a first in, first out process beginning with the start of a data transfer. Such a transfer is initiated in the next program line, which sets the SC register, serial transfer control, to the value OXFF. The meanings of all bits that are now set within this register can be inferred from figures 47 and 48. As soon as the 7th bit of the SC register is set to 1, our Game Boy automatically starts transferring the byte that rests in its SB register. Conventionally, the completion of this transfer is also inferred from a simple query of the 7th bit, since our SM83 CPU automatically resets its value back to 0 once a complete byte has been sent via the game link socket. However, it was mentioned earlier that the data transfers, especially on the DMG CPU hardware, require a lot of time for their completion. Yet, for the accurate parsing of a MIDI file's contents, the limitations of all program tick times should be adhered to as closely as possible, and any large tick duration exceedances stemming from an overly long wait for the completion of a transfer should, therefore, ideally be compensated later on by omitting the wait times of subsequent ticks. Accordingly, a mechanism for tallying the transfer times is also required at this point, which makes the following wait process somewhat more complex. As soon as a byte transfer has been initiated for a modification of the SC register within the above code, the wait after byte send function is called to interrupt the program's execution. In all cases, the program waits for the exact number of TIME ticks that was previously defined in the wait ticks between sends variable. However, the purpose of this function call is not only to wait for a transfer of a single byte to be fully completed, but also to give all MGB instances of the linked Game Boys enough time to receive and evaluate the sent byte. Logically, this wait period after the transmission of a MIDI byte takes up a considerable amount of time, which is why our TIM-A register often overflows when transmitting multiple events within a single tick. In order to minimize the resulting errors in the timekeeping of our program, the wait after byte send function contains within itself several mechanisms for dealing with TIM-A values close to the overflow limit. The excerpt from the function code shown in figure 49 illustrates this. As can be seen from the program code of the wait after byte send function in figure 49, this function has a return value which is added to the current value of the has elapsed time limit variable within our playback loop. Intuitively, the return value of wait after byte send tells us whether the time limit previously calculated for the duration of a single program tick has been exceeded during the current waiting period. Since the original Game Boy in particular is low in its output of MIDI bytes, such timeouts occur rather frequently on the DMG CPU. To prevent this low data output from affecting the speed of our final playback, our loop must later on ensure that all exceeded time is somehow made up again. But first, the transmission of the second byte commences in our main loop as soon as the wait time following the transmission of the first byte has elapsed. To make sure that the proper byte is sent out, the address value of the event data pointer is increased in the first line so that it now points to the newly created byte. Aside from this incrementation, however, the actual mechanisms for transmitting the second and third MIDI bytes are identical to those of the first byte, and therefore there is no need for them to be explained any further. Once all 3 bytes of the MIDI note messages have been sent out, the event data and event timing pointers of the tracks must both be incremented one final time. This ensures that the address values of the track's 2 stored pointers are directed to the data and timing values relevant for the next event in the track sequence. With that, the entire note event has been parsed. As mentioned above, only one other MIDI event type is processed by our program in addition to the 2 note messages. Specifically, these are the set tempo meta events, which, as their name suggests, are used to change the playback speed of a MIDI song. For this purpose, the status byte of this meta event is followed by a sequence of 3 data bytes instead of the usual 2, which together represent the new tempo value. The code section in figure 50, which deals with the processing of tempo meta events, shows us that a new tempo value can be obtained through the sequential shifting of all 3 data bytes into an empty UN32T variable. Once the new song tempo has then been determined using this method, it can then be used for the necessary timing calculations in exactly the same way as the standard tempo value. A new needed increments value is subsequently determined using the same calculation steps which were previously explained above. Since this new tempo value only affects the speed at which the following MIDI events are parsed by MIDI-BOI, the bytes of the meta event do not need to be sent out to the other Game Boys in our system. This means that after increasing both pointer values, this part of the program can be exited immediately. However, it should be noted that MIDI-Dumper-GB adds 2 additional OXOO data bytes to the 4 event data bytes of the set tempo signal type, and that the corresponding event timing value is also stored twice. This padding process is primarily used to maintain a uniform formatting of all signals, for which each event timing may be assigned to exactly 3 bytes from the track data array. Accordingly, the corresponding event data pointer must be increased by a total of 6 UAT addresses, and the event timing pointer by 2 UAT32T addresses after we're done processing our set tempo event. As the code snippet in figure 51 shows us, the currently relevant event data pointer is increased by a total of 3 byte addresses for all remaining MIDI signal types, while the event timing pointer is increased by 1 UAT32T address. At this point, it obviously doesn't matter if a signal wasn't previously handled in the above program code, since we still might want to potentially handle the next event of the track and therefore need our pointers to be set accordingly as we move on. Since the else block guarantees that we obtain the correct pointer addresses for the next MIDI event of a track in all scenarios, the following code snippet can now execute a preliminary evaluation of the next event data. To begin with, we check whether all events of a track have now just been sent out simply by comparing the value of the next MIDI event status byte to the value of the status byte OXFF, which MIDI-Dumper-GB artificially appends to the end of each data array. The negated return value of this comparison query is then stored in the track's unfinished array under the index which corresponds to the presently handled track. Next, the ROM bank containing the event timing array of the current track is loaded once more into the memory area addressable by our Game Boy for a call of the just_switch_bank's event timings helper function. Once this call has taken place, the while block of our do-while loop can be used to check whether the termination conditions have been met. At this point, our goal is to run through the above do-while loop either until all MIDI events of a track whose event timing match the current timer value have been parsed, or until the end of a track has been reached. The first of these conditions can be evaluated by simply comparing the timer value with the event timing of the next event, and the second by looking at the stored track's unfinished value. If there are no further MIDI events to be played within a MIDI track during the current time step, then the above for loop now also runs through the remaining tracks of the MIDI file while executing the same procedures just described above. Only once all tracks have been completely processed in this present tick does the for loop, together with the current program tick, terminate, at which point the code section shown in figure 52, which ensures the proper timing of our playback, is executed. After exiting our program tick loop, MIDI-BOI will first deal with some potential user input, however. To do so, it first checks for any user input by storing the return value of the joypad function into the previously declared joy state variable, and then uses an AND statement to determine the actual button that was pressed, if any. By pressing the B button, the user may pause the playback of a MIDI file. In our case, the pause simply works by us saving the current value of the TIM-A register into the song pause time variable, after which point we enter an idle while loop, which we will only exit once the user has pressed the A button. Upon receiving the A button pressed to unpause the playback, the TIM-A register is restored to the previously saved song pause time, at which point all further parsing work can simply resume as usual. Alternatively, the user may also press start to end and subsequently restart the playback of a song. To achieve this functionality, we simply free all of our data arrays and then leave the play pre-parsed tracks function once the user has pressed the start button. Now, the previously declared but not yet explained variable timer quotient is calculated by dividing the current value of the TIM-A register by the calculated number of TIM-A tick increments that correspond to the duration of a program tick. Since C never rounds up when executing integer divisions, we know that the time limit of our program tick has been adhered to when the value of this division, as well as the value of the has-elapsed time limit variables, are both exactly 0. In such a case, however, the time limit may also have been undershot, which is why our program is set to wait in an empty while loop until the TIM-A register has reached the value of needed increments during all such occasions. Afterwards, TIM-A is then manually reset to the value of OXOO simply to make all timekeeping during the execution of the following code more efficient. However, if either of the two time-holding variables mentioned above contain a value of at least 1, then our program may not wait at this point, since the execution of the current program tick has already exceeded its time limit. To make up for the lost time in the event of such a delay in playback, all wait instructions are suspended for the upcoming program ticks until the variable has-elapsed time limit once more contains the value 0. To ensure that has-elapsed time limit does eventually go back down to 0, its value is subtracted by 1 after each program tick without waiting, yet also increased by the value of timer quotient. This ensures that the missing waiting period in program ticks that have already exceeded the time limit is not incorrectly interpreted as our program making up for lost time. Another if query in this code block then checks whether timer quotient has a value greater than 0. In such a case, the duration of needed increments is subtracted from the value of the TIM-A register so that the timekeeping algorithm is protected, as far as possible, from an undesirable scenario in which the TIM-A register overflows from OXFF to OXOO outside of a wait after byte send function. In a final line, the timer variable is now increased by the consolidation value at the end of a program tick. This always forms the final operation required to process a single MIDI-BOI time tick. If our file still contains unprocessed MIDI events at this point in time, the entire loop above is executed once again for the next program tick. Only after all MIDI bytes of a MIDI file have been processed using this method does our program finally exit this while loop, free its pointer arrays, and shortly thereafter return to the infinite while loop in its main function, ready to play the file back once more if the user so desires. At this point, the complete process for playing a MIDI file on the Game Boy hardware has been explained in detail. Of course, a third test of how well or poorly the above procedures perform in a real-world scenario when outputting MIDI files is still pending. The next chapter will therefore describe the setup of a controlled test environment in which all of MIDI-BOI's capabilities can be verified for the first time. And thus ends the short little reading segment. I hope you enjoyed and could follow along with my explanations of MIDI-BOI and MIDI-Dumper-GB. In the next chapter, we can now finally turn our attention towards testing the capabilities of this two-software solution, but before that, I'd like to add one final note on the topic of the consolidation factor. As I've explained within my master's degree, the consolidation variable of MIDI-BOI is used to consolidate several standard MIDI ticks into longer program ticks, in a process which is supposed to reduce the amount of wasted CPU cycles that our program would otherwise spend on parsing empty MIDI ticks. For this consolidation process to work without skipping any MIDI ticks containing events, or breaking the entire parsing algorithm altogether, however, several factors need to be taken into consideration when choosing a consolidation value. First of all, the consolidation factor needs to be chosen so that the duration of a consolidated MIDI-BOI program tick throughout the entire playback of a song never exceeds 254 times the tick rate of TIM-A, as the timekeeping algorithms will otherwise break. On the DMG CPU, this means that a consolidated tick may not exceed 15,500 microseconds, while a consolidated tick on the CPU CGB may not be longer than 7,751 microseconds. To calculate the duration of a consolidated tick, you have to divide the different tempos of a song, read out from the hexadecimal data bytes of the tempo change meta events from the track 0 data array, by the time division factor, and then multiply the resulting microsecond value by the consolidation factor. However, since longer MIDI songs can contain tens or even hundreds of such tempo change events, calculating the optimal consolidation value can quickly become tedious beyond reason. This problem is further exaggerated by the fact that the consolidation value also needs to cleanly divide every event time of every event of the song, since all event times whose event timings aren't hit at a point of the parsing process are skipped by MIDI-BOI. We don't actually check if an event timing lays in the past, simply because the performance of 32-bit smaller equals comparison operations on the SM83 are downright horrible. Indeed, if you look at the code covered so far in this chapter, you may note that MIDI-BOI only ever uses equals or unequals operators instead, and for good performance reasons at that. So, in summary, a properly chosen consolidation value needs to be bigger than 1, as consolidation is otherwise effectively disabled, needs to always be shorter than 15,500 or 7,751 microseconds, and at the same time it needs to also divide all event timings within a song evenly. As you can probably guess, the effort of calculating a perfect consolidation factor can quickly turn maddening, so I'd like to offer you a few bits of advice at this point. The biggest of these pieces of wisdom that I can impart on you is this: simply don't touch the consolidation factor if it isn't needed. Just change it once to 1 after downloading the GitHub repository, and then leave it until you encounter a song that doesn't play at full speed. On the CPU CGB, this happens virtually never, at least as long as you're sticking to standard non-black MIDI files. So far, I myself have only encountered a single song that doesn't play at full speed on the CGB with a consolidation factor of 1, cavestory.mid. But with how egregious the waste of MIDI tick cycles within that song is, this performance struggle shouldn't be much of a surprise. No other MIDI file that I've tested up to this point has been quite as awful in its timings, and I therefore expect that you should only run into files that need a consolidation value on the CGB once every blue moon. On the DMG CPU, the story is a bit different, of course. Because of how slow its signal transmission rate is, all but the most simple MIDI files will need a consolidation factor when being played on the original Game Boy. To quickly find a consolidation factor in all such cases, I suggest the following workflow. First, check one or several track C files which contain many events, and therefore many corresponding event timing values. Usually you can quickly make out a prime factor, 2, 3, 5, 7 or similar, which evenly divides all event timings of all tracks. Simply use a calculator and try around for a bit, and you should come up with one in short order. As soon as you have your hands on a number of possible prime factors, together with their multiples, You can simply use the lowest one, compile your MIDI-BOI ROM, and then check if the file plays back at full speed. If it doesn't, move on to the next larger prime number or its multiple until you find a factor which works, or until your factor exceeds roughly 25. Usually, any consolidation factor larger than 25 will result in program ticks that are too long, meaning that checking any larger values will generally just be a waste of time. If your song doesn't play back at full speed by the time you're considering consolidation values larger than 25, then it's highly likely that the MIDI file is simply too complex to be parsed on the DMG CPU. A slightly simpler, though more labor-intensive approach to finding the right consolidation factors still can be extracted from the following flowchart. If you don't want to bother with finding prime factors and their multiples, then you may also simply try every value between 2 and 25 in order. Since MIDI-BOI will need to be recompiled and retested after each change of the consolidation factor, this methodology obviously requires quite the time investment, but it does allow you to skip any and all mathematic calculations if those aren't your thing. A combination of the two approaches just laid out above should hopefully allow you to find a working consolidation factor in the event that your song requires one. If you'd like to find out more about the consolidation factor or would simply like a summary of all the information I've just covered, you can visit MIDI-BOI's GitHub repository and read through its README file. There's an entire section on consolidation in there. Otherwise, I think the two of us are both more than ready to move on from this topic, wouldn't you say? Indeed, I think it's just about time that we finally get into testing MIDI-BOI for all this little program is worth. So without further ado, why don't I let my program take over for a bit, so that it may simply speak for itself. As the previous videos have just shown you, even the original DMG-01 Game Boy can handle a playback of basic MIDI files thanks to the shared powers of MIDI-Dumper-GB and MIDI-BOI. However, there are clear limitations to its playback capabilities. Here's a short recording of my Game Boy playing a MIDI file of the song Carnival from the Homestuck album Cherubim through an older version of MIDI-BOI still without its UI at the time. This following clip should give you a decent impression of just how bad things can sometimes get, even with a maxed out consolidation factor. While you should be aware that the MIDI file in question is not actually compliant to the MIDI standard, as it uses far more than 16 voices at a single time, you can obviously hear a significant slowdown in the playback speed, which isn't great. Interestingly enough, the limiting factor of the DMG's MIDI parsing capabilities isn't actually the SM83 processor itself, as that little CPU actually performs sufficiently well to the point where it can handle pretty much everything but black MIDI files, as well as a few songs with very long pauses or very slow tempos. Instead, the biggest issue of the DMG is its anemic clock signal frequency, which inevitably causes the handheld to fall behind in its signal processing tasks. This is because we currently wait for the transmission of all 3 bytes of a MIDI event to be completed before we move on with the following signal processing work. Of course, this means that there still is a lot of room for improvement here. The introduction of an asynchronous data processing and transmission wait system would massively boost the MIDI parsing performance to the point where the DMG should hardly struggle with any common MIDI files. But obviously there's a fair bit of complexity in implementing such a thing. I'll talk more about my thoughts of working on MIDI-BOI in the future later, so for now, let's first take a look at how the Game Boy Color performed. Here's a video of the Game Boy Color playing the Cave Story theme. As expected, the Game Boy Color doesn't struggle in the slightest with a task which even the original DMG was able to handle just fine. Now, how well did it do with playing back Carnival? Well, take a look for yourself. Thanks to the increased transmission speed and its double speed mode, the CGB CPU SoC performed significantly better at all MIDI parsing tasks across the board. Using a Game Boy Color as my parser and 2 DMG CPU-based Game Boys as slaves running MGB, I was able to achieve results that were shockingly acceptable and far better than anything I would have ever imagined a Game Boy being capable to produce. That having been said, the results still aren't necessarily perfect. Beside the low clock speed that hampers the DMG CPU, there's also the topic of timing to consider. At a resolution of 16 kHz, using TIM-AAiS incrementation rate for timekeeping generally produces pretty competent results, but there are issues. Since the duration of a MIDI tick usually doesn't divide itself well with the duration of several TIM-A register ticks, you may be left with a scenario in which the duration of a MIDI tick within MIDI-BOI deviates from its actual value by up to half the duration of a 16 kHz register tick. In this worst case scenario of the MIDI tick being half a register tick too long, our Game Boy MIDI playback will gradually drift out of sync with the actual recording at around 30 microseconds per tick on the DMG and 15 microseconds per tick on the CPU CGB. In the case of the Cave Story theme MIDI file, we play back our song with a tick duration of 992 microseconds, meaning we play around 1008 ticks each second. In this configuration, we could suffer a maximum drift of 1008 times 30 microseconds, or around 30 milliseconds each second, assuming we're not using any tick consolidation. After just a minute of playback, our song could then be up to 1.8 seconds out of sync with the original. Of course, in my experiments, I've consistently measured an error that is far less severe than that on both the original DMG and CGB CPU SoCs, simply because the tick error will usually be far removed from the maximum, and because the consolidation factor tends to slightly improve the drift since we're dealing with fewer, longer ticks. Still, there's clearly room for improvement here as well, although implementing any significantly more complex timekeeping algorithms will necessarily come at great expense to the CPU time. Since the next highest iteration rate of TIM-A is already 4 times faster than the one presently in use, we'll have to spend significantly more effort constantly checking TIM-A and keeping it from accidentally overflowing without our notice. That isn't to say that it can't be done or that such a change wouldn't result in a better playback experience, but the work required for what is presumably only a marginally better adherence to the tick duration of a MIDI song may very well not be worth it. Still, despite all the problems I've pointed out, and despite all the issues which remain to be fixed in the future, we're left with a surprisingly functional and acceptably accurate MIDI parser at the end of this section. There are, of course, a lot of thoughts still in my mind about this entire endeavor and about the results I've achieved. So why don't we dedicate the last part of this video to a final evaluation of the MIDI-BOI story. So, with the story of MIDI-BOI now well and truly told, why don't we go over some pros and cons before I share my final thoughts on the long, sleepless story which has brought me to this point. In its current state, there are some undeniably cool things that MIDI-BOI does, which I'm pretty proud of having brought about. For the first time ever, you're now able to play MIDI on a Game Boy, and despite my general history of creating user experiences which aren't as much user-friendly as they are user-hostile, MIDI-BOI is actually surprisingly easy to use, save for one very obvious exception that we'll get to in a second. MIDI-BOI also supports a decent range of MIDI files and MIDI file types, and once you've compiled the ROM for your file, you're pretty much ready to go. Since you no longer need a MIDI interface to play back the file, all that remains for you to do is to connect the Game Boys of your playback system via a GameLink cable or adapter, then to start MIDI-BOI on the host and MGB on the receiving Game Boys, and finally to start the playback of MIDI-BOI by pressing the A button. It really doesn't get any simpler than that. And as a final plus point, MIDI-BOI also supports MGB Hydra by default, so you can tune the listening Game Boys to any channels of the file which you want to hear be played. However, for all the positives, there's also a decently long list of problems which presently remain unsolved. The most obvious of these is that many larger MIDI files will lag on a DMG CPU, which isn't great. While most of these problematic files do playback on a CGB CPU SoC without further issue, you'd obviously want all Game Boys to play all MIDI files perfectly. Furthermore, there's also the problem that you can't currently play a MIDI file on a single Game Boy. Instead, you'll have to hook up additional Game Boys via the GameLink port, which obviously comes with its own costs. Now, since we already do deal with standard formatted MIDI signals within MIDI-BOI, I wouldn't imagine integrating the functionality of MGB into MIDI-BOI as too difficult of an undertaking, although the workload would inevitably be rather immense. However, should a merger of MGB and MIDI-BOI one day take place, then MIDI-BOI would not only turn into a much more useful project, but also presumably increase its performance, since fewer MIDI signals would need to be sent out via the GameLink port. Next on the problem list sits the consolidation factor, which is obviously very annoying to work with. Writing a simple Python PowerShell or batch script to automatically calculate the consolidation factor and write it into the MIDI-BOI.c file shouldn't be hard either, but so far I've been dragging my feet with that. Of course, without any such script at hand, there's still a decent bit of effort involved in getting MIDI-BOI up and running. In a worst case scenario, you'd have to recompile MIDI-Dumper-GB entirely, then execute MIDI-Dumper-GB, change the batch or CMake files in the MIDI-BOI folder, swap out the MIDI files, calculate your consolidation factor, write your consolidation factor into the main.c file, and only then are you able to compile your own version of MIDI-BOI. This amount of work obviously won't make anyone happy, let alone any non-programmers who've never even opened a Windows terminal before. Finally, there's also the issue of the MIDI playback timings not being perfect, but I've already talked about some possible remedies and the drawbacks that come with them before. Which obviously begs the question of what can and will be done in the future to improve MIDI-BOI. Well, since MIDI-BOI is actually quite easy to work with once you understand its inner workings, expanding its functionality should actually be quite easy. A lot of the possible improvements I've mentioned before could all probably be implemented in a few days or few weeks' time. The implementation of a proper asynchronous job system would obviously make for the biggest and most significant of these improvements, since it would not only improve the performance of the resulting MIDI playback, but would also lay the groundwork for other routines to run in the background, while MIDI-BOI waits for either a MIDI tick to pass or for a byte to be sent out. Indeed, I've already conceptualized several ways in which such a system could function, but there's a big problem that's been keeping me from putting any more work into MIDI-BOI. The fact that I now need to get a job. That's right, since my master's degree is now officially completed, my insurance company came knocking without delay to remind me that I'll be paying the full cost of my adult medical coverage, job or no job, starting on the 1st of October, which was very nice of them to do. With that threat in mind, you may understand why the rest of my year is essentially occupied by my scramble to find a workplace, an apartment, and a car to transport me between each. Sadly, there really hasn't been much time for me to work on my projects in recent times, as you'll probably have noticed. But okay, moving forward half a year or so, is it likely that I'll keep working on MIDI-BOI once my schedules free up again? Well, I'll answer that question with a resounding maybe. The big elephant in the room is that MIDI interfaces like Arduino-BOI and Mapico-BOI simply continue being the best solutions for MIDI file playback on the Game Boy. Not just because of their more accurate signal timings, but also because they allow you to use MIDI devices in addition to MIDI files. Now, thanks to MIDI-BOI, you're no longer required to purchase such an interface if you're solely intent on playing MIDI files, but for all other tasks, there's still no getting around buying a proper MIDI interface. Really, it was a ton of fun exploring all the different ways of getting interconnected MIDI playback working on different Game Boys, but for now, I think I'm burned out and done with this stuff. At least for the next few months. After that, who knows what'll happen. If any new developments in my realm of Game Boy MIDI work do occur, I'll most certainly make more videos on this channel to keep you updated, so if you're interested, feel free to subscribe. Otherwise, I'd still like to thank you very much for watching this video and giving this silly little project of mine the time of your day. Now, if you'll excuse me, I need to go find a job before an insurance shark repossesses my parents. Next time we'll see each other, I'll hopefully be employed and making mad bucks, because otherwise I'm pretty sure I'll have to live out the rest of my days in indentured servitude to the German pension system. Until then, though, this has been AP, signing out. Have a good one.